All right, in this video, I wanted to do one more example of a torque problem. So in this problem, we have a ladder that is leaning up against a wall. And of course, it's also touching the ground here. I said touching the ground. There we go. So on this ladder, we also have a person standing on it. And we'll plug some numbers in a second. But what we know is that the ladder is in equilibrium. And what is the minimum coefficient of friction required to keep the ladder from slipping? So I'll give you some numbers, and then we'll talk about the free body diagram, and then we'll do the problem. Okay, so let's say that the ladder is 3 meters long. So the whole ladder is 3 meters long. The person is 2 meters up the ladder. The person has a mass of 50 kilograms. The ladder has a mass of 20 kilograms. The angle between the ladder and the floor is 75 degrees. I'll write this down. So the person is 2 meters up and has a mass of 50 kilograms. The ladder is 3 meters long, has a mass of 20 kilograms, and I will say here is uniform or of uniform thickness, or however we want to say that. That gives us a hint about something on the free body diagram. And it is at an angle of 75 degrees with the floor. Okay, so first let's draw the free body diagram. And as a part of that, I want to look at this idea of friction and show that we know that we do need friction here just from the free body diagram, even if we don't know anything else. So I'll leave the picture up, but I guess I'll write, ultimately, we are looking for our friction coefficient. So I'll leave that up there, and we'll be back to talk about that in a little bit. Okay, so free body diagram. This is, we haven't had that many free body diagrams that are objects that aren't horizontal. So we want to draw our object as a line. And here the ladder is at this 75-degree angle. So our free body diagram is also going to be at that 75-degree angle. And now we want to identify things that are touching the ladder, right? So we have the ladder touching the wall there. We have the ladder touching the floor here. And we have the ladder touching the person there. So these are all potential contact forces that we could have on our free body diagram. Let's look at the person first. So the person is being pulled down by gravity. So they're acting as a weight, a downward force acting on the ladder. So that is going to be a force acting at this place where the person is, and that is downward. So we'll call that F person. That's really, that's the force of gravity on the person that then is being transferred to the ladder, but we'll just call that the force of the person. The ladder is also touching the ground. So what kinds of forces could we have there? Well, we might have a normal force, or well, we definitely are going to have a normal force. And the claim is that we're also going to have potentially some force of friction here. And we don't know if it's going to be to the left or to the right. I'm just going to guess it's to the left, and we'll check that in a second. So I'll say friction. And note, since this is in equilibrium, we know this is not moving. We do know that this is static friction, although we're not making a distinction between those in this problem, so that's not a big deal. Okay, other forces. The ladder is also touching the wall up at the top there, which means that we have another, normal force surface happening there. So we're going to draw a normal force there. And potentially you could imagine there also being a friction force there. It turns out a friction force is not necessary there, so we're gonna leave it off, and I can explain why that is later on. Since we have these two different normal forces, and they do not have to be the same size, I'm going to label them. I'm going to call this one normal force 1 and this one normal force 2. So Fn1 and Fn2. Okay, these are all of our contact forces. There is one more force left, and that is the mass, or the weight of the ladder itself. So that is another force acting at the center of mass of the ladder. Remember, the ladder is uniform, which means the center of mass is in the middle, 1.5 meters up, and that is the force of gravity. So 1, 2, 3, 4, 5 forces on our free body diagram, and ultimately we want to find out the friction coefficient. And so we're going to want to look at, if that's happening at the bottom here, we need both of these forces in order to calculate that, right? So the friction force here is equal to mu times the normal force at that surface. So if we want mu, we need both of those, and we need to find the ratio. So that's our goal here. All right. So before we do anything else, let's just do a quick check of our forces. And I'll show you why we're doing this in a second. So the sum of our forces in the y direction have to be 0 because we're in equilibrium, right? So is this possible given this diagram? Well, we got a normal force up, we got one gravity down, and we got another weight of the person down. So yeah, I could imagine those adding up to 0. That looks doable. If we look at our forces in the x direction, if we do the same thing, there's something kind of funny going on, right? I have this normal force to the left, and we know it has to be to the left because it has to be perpendicularly away from the wall. But I've drawn this friction force to the left also. And the way I've drawn these, they cannot add up to 0. So this is our clue that I have incorrectly guessed the direction of that friction force, which is totally fine. Now's a good time to catch that. But if we had proceeded with the problem and not solved that, we would have just ended, or not fixed that, we would have just ended up with a minus sign later on when we tried to find what this friction force is. So no big deal, but we do know enough to fix this now. Okay, so these are all of the forces on the free body diagram. Since we're here, I will explain briefly why we don't need a force of friction here, up or down. And the reason is we already have this normal force that is as big as it needs to be to make the y acceleration 0. And that means an additional static friction force that is also as big as it needs to be to make the y acceleration 0 is redundant. And the normal force here is going to be doing the job of that. I'm very unlikely to give you a problem on a test where there is that kind of potential overlap. So this is an extreme case for this course, and in general, things will not be this ambiguous in terms of like whether there's a friction force here or not. So I will, pretend it said in the problem statement, there is not friction right here, and that's just something we can take for granted. Okay, so we have these two equations. We could use these to make some statements about how big these forces are. So let's go ahead and do that and write down some equations. So in the y direction, we have our normal force up, gravity down, and the weight of the person down. So that means that this equation tells us that Fn2 minus Fg minus F person equals 0. All right, in the x direction, we have the other normal force and our friction force. So here we have friction force to the right, positive direction, minus Fn1 to the left in the negative direction equals 0. So these now are two equations that tell us relationships between how big those forces are. And that's the last we'll need of our force equations. So I'm going to erase them just to save some space. Okay, so now we're ready to actually find some forces and what's going on here. So before we do that, I'm going to label a couple things on our diagram. We know some distances that are going to come in useful. So remember, this whole ladder is 3 meters long. From the bottom to the center of mass is 1.5 meters. And from the bottom to here is 2 meters, which means this is 0.5 meters. And this is 1 meter. I guess I don't need the meter sign. I'll just put 1.0. So we know what all of those distances are. And we know some angles also. So if this is 75 degrees, then this angle and this angle are the same. Those both have to be 15 degrees. And this is also 15 degrees. And this one up here is 75 degrees. I'm not going to draw that in because I don't quite have room the way I've drawn it. Okay, so now let's move on to our real equilibrium equation, that is our torque equations. So remember, the sum of our torques has to be 0 for any rotation point. So what we're going to do is, I'm going to move this over here. We ultimately want to find this friction coefficient. Like I said, our static friction is equal to normal force 2 times mu. So mu is equal to our friction over normal force 2. So we need to know how big both of those are. The friction force we actually have in this equation already. And if we rearrange this equation, it just says that the friction force is the same size as normal force 1, right? We have that much force to the left, that much force to the right. They have to be balanced. So because of that, this is equal to normal force 1 over normal force 2. And now that means that our real goal, or our more immediate goal here, is to find what these two forces are. Okay, so yeah, let's get to work. Normal force 2. We'll start with normal force 2 because it's easy. We have it in this equation in the y direction. So that is normal force 2. If we rearrange this, is equal to the force of gravity on the ladder plus the force of the person. And we know both of these pieces, right? The force of gravity on the ladder is mg, so that's 20 kilograms times 9.8, plus the weight of the person, so that's 50 kilograms times 9.8. So that's 70 times 9.8, which is 686 newtons. So that is Fn2, and that we got from this. So here's a recap. This equation told us that the friction and the normal force 1 were the same, so we need to find normal force 1. This equation told us that, balancing things in the y direction here, normal force 2 was equal to these two combined, and we actually happen to know those, so we know normal force 2 is 686 newtons. Okay, I'm going to write that over here to make more room, and now we're ready to do the fun part. So now we need to find normal force 1, and we need to do that without knowing what this friction force is, right? So I guess my point is, if we're going to use torque for this, if we were to pick a point, say in the middle, to sum our torques around, we're going to get a torque from the normal force and from this force, but we're also going to get a force from friction, and we don't know how big this is. There would be a way to solve that equation, but it's just going to be slightly harder than picking a different point. So it turns out, as I've mentioned before, it is advantageous to pick a point with a force that we do not know, because then that will not appear in our torque equation. So if we pick this point down here, let's see what happens. So if we use this as our rotation point, let's sum the torques around that lower left point. So there, we have a torque. I'm just going to label 1, 2, 3, 4, 5 torques that we have. So that's the torque from N1, the torque from the person, the torque from gravity, the torque from normal force 2, and the torque from static friction. Okay, so the torque from N1, we don't know, we don't know how big it is, but we can at least write an equation that that includes that information. So all of our torques are RF perpendicular or RF sine theta, as long as theta, remember, is the angle between R and F. So let's go through these in order. So normal force 1, the torque from normal force 1 is equal to R, the distance, that is 3 meters, times the size of the force, so that's just F N1, times sine theta, the sine of the angle between R and F, which is our 75 degrees. So this is times the sine of 75 degrees, and that is our first piece. Oh, I forgot. Is that torque going to be positive or negative? So if we have a force like this acting on an object like this, that is going to act to rotate it counterclockwise. So indeed, that is going to be a positive torque, and we did not need a minus sign there. Okay, let's continue. So that's this one. We have the torque from the person. So that is going to be clockwise. So that is negative. So we can start with that. So we have minus the torque from the person. So that is a distance of 2 meters away. And we know that force is 50 times 9.8, the weight of that person, times the sine of the angle between them, and that is 15 degrees, the sine of 15 degrees. Okay, so we did the torque from normal force 1. We did the torque from the person. Now we need the torque from gravity. So that's going to look the same as the person, just with different numbers. Yeah, what I mean by that is it's also negative. It's also sine of 15 degrees. So we have minus 1.5 meters now times the weight of the ladder. So that's 20 times 9.8 times, again, the sine of 15 degrees. And then we're done with the torque from gravity. Okay, last two, the torque from normal force 2. Well, normal force 2 is at our rotation point, right? This is the floor pushing on our rotation point right at the rotation point, which means R equals 0 for that one. So this is 0. That's also true for the friction force, right? This is also a force acting at our rotation point. So this is also a torque of 0. And so these two never really mattered in that equation. And that's why it's convenient to use this point. We only end up with 3 torques in our equation that are not 0, and only one of them we don't know. So that makes this, easier to figure out than other possible points. Okay, so if we plug some numbers in here, we get the following. Let's stretch this out. So we have 3 times the sine of 75 degrees times normal force 1. So that is our unknown. And we also have the first one here is minus, if I plug that into my calculator, minus 253.6 Newton meters. The next one, this one is minus 76.1 Newton meters. And, I missed the big equation, right? The sum of the torques, that's equal to 0. So this whole thing is equal to 0. This whole thing is equal to 0. And so these are all adding up to 0. So I can now move these two to the other side. I get 3 times the sine of 75 degrees times normal force 1 is equal to 253.6 plus 76.1, which is 329.7. And now, so normal force 1 I can solve by dividing both sides by 3 times the sine of 75. I'm going to make some room up here. And so that is equal to 113.8 newtons. Okay, so we have normal force 1. All right. So before we go back to this, we've found all of our unknown forces. Well, yeah, we found all of our forces except for this friction force. I mean, I said the friction force was equal to normal force 1, but that's worth explaining for one more second here. But we found normal force 1 and normal force 2 for sure, unambiguously, which is the hard part. So we're almost done with the problem. So what I wanted to point out here is that because this is static friction, I wrote down this equation originally, but that isn't exactly right. I mean, it's an okay way to think about this problem, but if we're being very careful here, our static friction force isn't equal to that. It is less than or equal to normal force 2 times the static friction coefficient. So when we found, what we have found is we've found normal force 1 and we have found normal force 2, and we've said normal force 1 based on this diagram is the same as the force of friction. But this could actually look like lots of different combinations. And what I mean by that is if normal force 2, for any particular value of normal force 2, you could imagine having a really, really, really big friction coefficient and having an upper limit to your static friction that was really, really big, right? But what we're looking for here is the minimum friction coefficient that is required to keep the ladder from slipping. So what that means is if we have some giant friction coefficient that gives us some giant value in our inequality here, that still is going to work too. But as we make mu smaller and smaller, we're getting this limit lower and lower so that our maximum value of this friction so that the maximum value of the static friction is getting closer and closer to what it actually needs to be to keep the ladder from falling down. So the takeaway from that is the mu we're actually looking for, the minimum mu, is when this is an equality, is when the static friction equals Fn2 times the friction coefficient. So I just wanted to explain, why we were looking at this, because that is when this limit that we're looking for happens. It's okay if mu is bigger. I mean, in real life, it would be okay if mu was bigger because the ladder still wouldn't fall down, but we're looking for the mu that causes it to change from being able to be in equilibrium to not being able to be in equilibrium. Okay, so now we're ready for this. So mu is equal to normal force 1 over normal force 2. So that was 113.8 over 686, and that is equal to 0.17. And remember, mu is unitless, so we don't have any units on this number. This is our final answer. All right, so that is it. That is how to do a pretty. This is a pretty hard torque equilibrium problem, and there are some lessons in here about ladder safety. If you're using a single ladder, like not a ladder that looks like this that you like walk up the side of, but when you have to lean up against something, friction with the ground is super important. If you had set this ladder, I mean, if this is a legitimate life lesson, if you were setting this ladder in a puddle or something so that the friction coefficient here is lower, and you climb up the ladder, it is very possible that there is not enough friction here to keep the ladder in equilibrium, and this end slides out very quickly, and the whole ladder, falls down like that, and you don't want to do that. So anyway, this is your ladder safety lesson for the week or whatever. Be sure you have good traction at the bottom foot of your ladder, and also we could have shown this in the numbers. This limit is a little easier to meet if your ladder is steeper. So they say the rule of thumb I learned was that the optimal angle to put a ladder like this is when you reach out in front of you, standing at the foot of the ladder, your arms should be able to go straight out in front of you and be on the sides of the ladder. I don't know, I'm telling you this. If you're going to use ladders professionally, take a ladder safety training course. Ladder falls are like the #1 cause of workplace injury. Okay, that's all I have to say about that. All right, so hopefully this is a helpful example of these kind of torque problems. This will be the last one we see in lecture. In the next lecture, we're going to be moving on to oscillations and waves.